So we have already studied mean value theorem, which is for the function which is differentiable over open interval 1 times and it is continuous over the closed interval. So first thing is we will discuss today the extended mean value theorem. So extended, just a minute. Extended mean value theorem. So that says if we have, instead of f is differentiable 1 times, suppose f dash is also differentiable 1 times. So then that means f is double differentiable function. So then we can apply the mean value theorem on f dash. So what we get, we will see here that if f and f dash are continuous on closed interval AB, so f is also continuous, f dash is also continuous, and the function f dash is differentiable on the open interval AB. So criteria is similar to the usual mean value theorem, but now f dash is also differentiable. So then there exists a point C between A and B such that we can write FB as f of A plus derivative of A times B minus A plus, instead of f dash C here we will get f double dash C divided by 2 B minus A square. So this is kind of second order mean value theorem also, we can say. So you can see that earlier uh, we had for single variable mean value theorem, we had fb equal to fa plus f dash c b minus a, right? But now we have this equation for the second derivative. So this way basically we can differentiate the function as many times it is differentiability is given, and we can write f of b up to the function as many times it is differentiable, right? So let us see what it gives as an output. So if I write the polynomial p1x to be fa plus f dash a into x minus a. So this is a basically f dash fa is a some fixed number, f dash a is some fixed number, and x minus a is a in power of x. So that is a polynomial in x. And what, so that is basically this first part. And extra what we get is this term. So that we will write as a error. So error is e1x, which is nothing but fx minus this polynomial. Alright, so basically what we are doing is we are approximating the function fx by a 1 degree polynomial, and what we will get remaining that we call the function e1x. So then essentially what we get then by the above theorem, that is extended mean value theorem, what we get is modulus of e1 b. So we are evaluating e1 at b, so taking x equal to b here. So essentially what we get is we'll get modulus of f of b minus p1 of b, right? Just substituting x equal to b here. So now what is this quantity? This is nothing but f of b minus p1 of b. P1 of b is fa minus f dash a into b minus a. So fa minus f dash a into b minus a. Again, in p1x we are substituting x equal to b. So we get this quantity. And am I right? Sorry. So that is f of b, right? Sorry, I did mistake. This is f of b because we are substituting uh, x equal to b here.
सर वो तो ए ही आएगा ना, वहाँ पे एक्स थोड़ी ना है।
Uh, will it be a? Okay, right. You're right. So that should be a. So now what we will use? We will use now the extended mean value theorem. So let us go to the extended mean value theorem. So what it says is that, so you are right. So I did some mistake there. So there will be b only there. So what is our term? Our term is fb minus fa minus f dash a into b minus a. So what is this term? This is basically fb minus all these terms we are taking on the other side. So these terms will be negative. So we'll get fb minus fa minus f dash a into b minus a. So that is exactly that term, and on the right we will get this term. So essentially what we get from the extended mean value theorem is this equals to f dash c divided by 2 b minus a square. So you're right, it will be fb only, and now here we are using extended mean value theorem. And what is c? C is between a and b, right? So so this term basically we can estimate if our function um, is good enough. So for example, if our function has second derivative which is continuous, then what we get is we can find the maximum value of the function, right? And that will be that will be m, right? Our function, suppose it is a good continuous the function who has a second derivative which is also continuous. So then we know a known result that any continuous function on the closed interval assumes the maximum value. So that maximum value we are saying m. So then what we can do, we can modulus of f double dash t is less than equal to m. So then we get this quantity modulus of e1 of b, which is uh, less than equal to, because now we are estimating f double dash c by m. So this will be less than equal to m divided by 2 into b minus a square. So the error basically we have estimated by maximum value of the function f double dash and the length of the interval, that is b minus a. So now if we take b approaches to a, that means the length of the interval basically goes to 0, then what we'll get is this approaches to 0, right? Because b approaches to a, so this number goes to 0, and this is a constant number. So this is basically the error approaches to 0. Then what we'll get? What is error? Error is the difference between function and this polynomial. And this polynomial is nothing but equation of a of a line, right? Because it is of the form a plus bx. So basically we are approximating the function by a line. Approximating the given function by a line. So it is called a linear approximation. So this this process is known as linearization. It has some applications also. But now basically we are discussing mathematical applications. So any doubts so far? Okay, so then we'll continue. So this polynomial, so now this is a remark that in general if the function is n times differentiable, then we get, instead of 1 degree polynomial, we'll get the nth degree polynomial. So then we get the polynomial Pnx to be fa plus f dash a x minus a plus second derivative by 2 factorial x minus a power 2 and so on. We'll get the nth derivative x minus a power n. So this is basically the generalization of P1x. So let us see what we have taken P1x. So P1x we have taken fa plus f dash a into x minus a. So that was up to first derivative f dash a. But now we have n times differentiable functions, so we extended it up to Pn. And what this Pn satisfies? It satisfies the condition that when we evaluate Pn at the point x equal to a, what we get is all x minus a terms will be 0 because we are substituting x equal to a. Finally, we will get f of a only the first term because other terms involve x minus a. And further, we can differentiate this polynomial k times, and then if we evaluate a, we will basically get it to be kth derivative of a. So this is true for each k such that 1 less than equal to k less than equal to n. So what is this symbol? This symbol is kth derivative of polynomial Pn. So you can check for k equal to 1, k equal to 2. You will be able to check that. And what will be the error term here? Error term is defined similarly. So we'll denote it by En of x. That is nothing but fx minus Pnx. So let us write down what is this. So this polynomial is known as Taylor polynomial. So this polynomial Pnx is known as Taylor's polynomial, and so what is basically Taylor's theorem? Taylor's theorem is extension of mean value theorem for the nth derivative. So let f be a function from closed interval a b to r, and we have f dash f double dash up to n minus 1th derivative be continuous on closed interval a b, and suppose the nth derivative exists. So we have not written nth derivative is continuous because anyway the function is differentiable, so it is continuous. So here we have not mentioned explicitly, but you can mention also. So nth derivative exists on open interval AB. So then there exists C between A and B such that we can write the expression of mean value theorem. So that is f b equal to fa plus f dash a into b minus a plus f double dash a. Now what we are getting is, here we are getting the factorial terms. So here 2 factorial will come. Later on we get n minus 1th derivative, n minus 1 factorial b minus a power n minus 1. And the last term will be in terms of c. So nth derivative at c, b minus a power n. So this is basically the the mean value theorem for the nth derivative. So let's take one example how these polynomials are useful. So this example is regarding estimating the value of square root function. So if you take m to be a natural number n, and we consider the interval, closed interval m to m plus 1, to r be a given function defined by fx equal to square root x. So suppose we apply the extended mean value theorem on this function. So apply extended mean value theorem for this function. So first thing is, what will be the closed interval here? So usually we take closed interval a to b. So what is a here? A here is, so here interval starts from m to m plus 1. So a is m and b is equal to m plus 1. Where what is m? M is a natural number, given fixed natural number. So later on we will fix. So basically we will fix m equal to 1 later on. So first of all, let us apply the mean value theorem. So mean value theorem will give us extended mean value theorem is f of b equal to fa plus f dash a b minus a plus f double dash c by 2 factorial is 2 b minus a square, where c is between a and b. So let us find out all these values. So basically b is m plus 1 and a is m. And for this, first of all, our function is square root x. So its derivative will be 1 upon 2 square root x, right? And the second derivative will be minus 1 divided by 4 x square root x, right? And these values we need to substitute for m and m plus 1. So also we have to substitute it for b equal to m plus 1 and equal to m. So finally, what we get in the extended mean value theorem is that we first write f of b. F of b means square root of m plus 1, right? Because b is m plus 1 and function is square root. Then f of a. So a is m, so we'll get square root of m plus what is the next term? That is f dash of a. So f dash of a means derivative at m. So derivative of m will be 1 divided by 2 square root m, right? And 1 is basically b minus a. So that is difference of m plus 1 and m, that is 1. Plus second term. Second term is 1 upon 2 factorial f double dash c. So f double dash is minus 1 upon 4x square root x that we have to evaluate at c. So we don't know what is c. We only know that it is c is between a and b. So a is m, b is m plus 1. And the difference of b minus a is 1, so it is 1 square. So this is what we get for the interval m to m plus 1. But now we want to evaluate for m equal to 1. So in particular, for m equal to 1. So m equal to 1 means our interval will be from m to m plus 1. So that means our interval now will be from closed interval 1 to 2. Right? So for m equal to 1, we get m equal to 1. So this will be square root 2 is equal to square root of 1, that is 1, plus 1 by 2. Square root 1 is 1, plus 1 by 2 minus 1 upon 4 c root c, where m is equal to 1. So 1 less than c less than 2. So in the previous formula, we just substituted m equal to 1. We are essentially getting this one. Now, if we use this fact that c is between 1 and 2, then we can estimate the value of the function. So that is what we want to do now. So since c is 1 less than c less than 2, what we get is 1 less than c root c, which is less than 2 root 2, right? So essentially, therefore what we get is, so from this we know that this is this number is basically 3 by 2, and here what we get is minus 1 by 8 c root c. Right, so essentially what we get is we get 1 upon just a minute. So what we get is square root 2 is 3 by 2 minus 1 by 8 1 by c root c along with 1 less than c root c less than 2 root 2. So after that what we get is our 1 by c root c. What is this term? This is nothing but minus 8 times root 2 minus 3 by 2. And then essentially what we get is this term is between is between 1 upon 2 root 2 and 1, right? So essentially what we get is 1 2 root 2 is less than minus 8 times root 2 minus 3 by 2 less than 1, and that will give us minus 1 by 8 less than minus 1 by 16 root 2. So this will basically give us an estimate that 3 by 2 minus 1 by 8 less than root 2 less than 16 root 2, and that will give us 11 by 16 root 2 less than 3 by 2 minus 1 by 16 3 by 2. So here what we have done is that this term we have approximated by 3 by 2. So what we are using is square root 2 is less than 3 by 2, right? Because we could take square on both the sides, then we get 2 is less than 9 by 4. So that is 8 is less than 9. So this initial statement we are using to say that this term is less than this term, right? So finally what we get is we are getting rational numbers in between the value of root 2 is that. So this value is roughly 1.375 and this value is 1.4583, and root 2 value we know by calculator that it is 1.4142, so on. So that is basically in this interval. So this interval we are getting using the extended mean value theorem and this particular estimate. All right, so we are using extended mean value theorem for the when the f dash is differentiable. That means function is 2 times differentiable. You can also apply the mean value theorem and get this such an interval by applying usual mean value theorem, and then you can do for the third derivative. So what we can observe there is that this interval will become smaller and smaller. So that is essentially the meaning of what we are saying here, that the error is basically going to 0.
Sir, in the left-hand side, it's 11 by 16. It should be 0.6875.
11 by 8 आएगा सर.
Yes, sir. 11 by 8 आएगा.
Okay, so maybe I am wrong. Yeah, so if you take the LCM, this will be 12 minus 1. Yeah, you are right. You are exactly right. So now just check whether this number is correct. 1.
Yes, sir, it's correct.
Okay, so that is I have done mistake in taking LCM. So this basically we are taking an approximation of this square root number without using actually the calculator. So nowadays anyway calculator is available, so we are able to do that directly. So this is essentially the Taylor's polynomial. Now if we
Excuse me,
go,
Sir, we can take any value of m na, or
so
least
m
value we
for,
have to take.
so in this example actually we have given which m we are supposed to take. So we have actually mentioned the interval,
Acha, okay, sir.
correct? Yeah, of course. If you want to practice, you can take any m and you can see. So that
sir.
m, it will change. Then that value will change root 2, root 3, and that way we can approximate different square roots.
Sir,
Yes.
why did we go only till second derivative? Means earlier we went till nth derivative
Nth
f
derivative.
s.
Yes.
Yes. So why
So
only we limited ourselves to second derivative here?
yeah. So what we have discussed is for the extended mean value theorem for the second derivative. You can also do that for the third derivative and do the same process. And you can use square root 2 less than 3 by 2 there also, and see whether we are getting any better interval.
Okay. Okay.
So
Thank you,
that
sir.
I'm keeping as an exercise. I will not do it. Okay,
Okay, sir.
but surely we can do that, and I you can observe that the interval will decrease. The length of the interval will go closer to 1.4142 from both the sides.
Okay, sir.
Okay, so let me go to the Taylor series. So Taylor series is basically the when the function is infinitely many times differentiable. See, so we have the function sine x, cos x, e power x. So they are differentiable as many times as we want. So can we expand them in terms of mean value theorem using all the derivatives? So that is basically the series expansion. So the series fa plus f dash a x minus a plus second derivative of a by 2 factorial x minus a square and so on. And the nth derivative will be, nth term will be this one. So this in the summation form we can write as summation n is equal to 0 to infinity nth derivative at a by n factorial x minus e power n. So here fn a is nth derivative and f0 a is basically f of a. So no derivative. So the given function. So this series is called the Taylor series of at around the point A. So if we take a equal to 0 in this, we get a special series. That series we say as a Maclaurin series. So if I take x equal to a, then what change will be there? We have to evaluate the function at f of 0, f dash 0, and these terms will be x, x square, and so on if a is equal to 0. So that particular series is known as Maclaurin series. So whenever we have a given function, we want to expand it in powers of x, then we will find the Maclaurin series because a is equal to 0. Then this will become x square if a is 0, right? So if you want to expand the series in power of x, we'll go for the Maclaurin series where a equal to 0. And we want to expand the series in powers of x minus 1, for example. So x minus 1, x minus 1 square, and so on. So then that series is known as Taylor series because a is not equal to 0. So if we want to expand as x minus powers of x minus 1, then a equal to 1 and the series is Taylor series. So today we will see the example of Maclaurin series. So let us take a function fx equal to sin x. Then find Maclaurin series expansion of this function. So since we want to find Maclaurin series, so for Maclaurin series, we take a equal to 1 equal to 0. So the series is, so first of all let us write down what is series. Series is f of 0 plus f dash 0 times x plus f double dash 0 by 2 factorial times x square and so on. So we'll write down the first 3-4 terms of the series and then we'll guess the general formula. So now given function is fx equal to sin x. So we know all the derivatives of this function. The first derivative will be cosine x, second derivative will be minus sin x, third derivative will be minus cosine x, and so on. And we want to substitute it at 0, all the derivative at 0. So what is first of all f of 0 is 0 because sin 0 is 0. F dash 0 is cos 0 is 1. Second derivative of 0 is minus sin 0, that is also 0. And third derivative of 0 is minus 1, and so on. So substituting these values in the series, we get, so what we get is we get the series expansion f of 0 plus x f dash 0 plus x square by 2 factorial f double dash 0 and so on. Let us find up to third term. So this will be f of 0 is 0. Just check f of, yeah, f of 0 is 0 plus f dash 0 is 1, so we'll get x. Then second derivative is 0 because it is in terms of sin 0. Third term will be x cubed by 3 factorial into minus 1. Third derivative is minus 1, and so on. So what we are getting here is we are getting the term x. This will be minus, so minus x cubed by 3 factorial. The next term will be x power 5 by 5 factorial. So here, so it is easy to see that these terms 1 minus 1 are changing the alternate sign. because the derivative of cosine is minus sin x. So we got this series expansion which we can write in terms of summation. So the general formula is summation n is equal to 0 to infinity. Since the sign is alternating, it will be in powers of minus 1 raised to n, and all the derivative coming is are odd numbers derivatives. So it is 2n plus 1 by 2n plus 1 factorial, and powers of x is also odd. So x power 2n plus 1. So this is general formula of this series. So basically, if we write this series as summation an, so then what is an? An is this nth term, and we want to see whether this series is convergent or not. So for that we will apply the ratio test, because here the series in terms of powers of some number. So usually we apply the ratio test there. Okay, so we substitute n equal to n plus 1. So this will be n plus 2n plus 3, right? N equal to n plus 1. Similarly, here we get x power 2n plus 3. Now, in ratio test, basically we apply for the non-negative terms, right? But here we have the powers of minus 1. So some terms are positive, some terms are negative. So therefore, we apply the ratio test with the modular sign here for this particular series to check the absolute convergence, basically. And then we know that every absolute convergent series is convergent. So essentially, we will get the series is convergent or not. So therefore, the ratio will be limit n tends to infinity modulus of an plus 1 by an, that is limit n tends to infinity. So an plus 1 is this term, into modulus of an, so that is minus 1 power n 2n plus 1 factorial into x power 2n plus 1 2n plus 1. So if we cancel the common terms, finally what we get is modulus of x square divided by 2n plus 2 2n plus 3. So now what is x? X is given real number, right? Because we are given the function f of x. So x is the variable. So we want to check for which particular value of x this series is convergent. So x, we have to substitute one by one. X equal to 0, x equal to 1, x equal to 2, so on. And then we'll see whether this limit is less than 1 or greater than 1. If it is less than 1, the series is convergent. And for greater than 1, it diverges. So for what values of x this series is convergent? So if, for example, x is 0, then what is limit?
सर नेगेटिव साइन नहीं आएगा क्या?
So we are taking modulus. So basically, minus 1 modulus is 1.
So I just understood. Okay, sir.
Right. So therefore, we have taken the modulus. So the minus, whatever power minus or plus will go away, because modulus of 1 is also 1, and minus 1 is 1, also 1. So minus 1 power n is also 1. So if you want, first you can write it is -1, but then -1 modulus is 1. So you can, in next step, you can remove that minus sign.
No, sir. Actually, I just forgot that it is modulus. Sorry.
Okay, anyway, so that is fine. Okay, so yeah, so we one by one substitute the value of x and see when the limit because the ratio test we are applying, so limit is less than 1, the series is convergent, limit is greater than 1, it diverges. So if we substitute x equal to 0, then this term will be 0, right? So limit will also be 0. If we substitute x equal to 1, then we'll get limit n tends to infinity 1 divided by 2n plus 2 into 2n plus 3. So in that case also limit is 0, right? So x, whatever fixed value you take, limit is always 0 for each real number x, fixed real number x. And right, and then we know that in the ratio test, whenever the limit is less than 1, therefore by ratio test, this series is absolutely convergent. And since it is absolutely convergent, hence it is also convergent. So we are using this result that if the series converges with absolute value, then it converges without absolute value also. Right. So we proved that this series, Maclaurin series of the sin x function, that is basically this series, is convergent for all values of x. So now there is a known result that therefore whenever this series converges, it equals to the value of the function at that point. So that means sin x equal to -1 power n x power 2n plus 1 divided by 2n plus 1 factorial for all mod x less than infinity. So mod x less than infinity means for all real numbers. So lastly, what I said, let me repeat. What I'm saying is whenever this series, which is Maclaurin series, whenever it converges for those values of x, it equals to the value of the function. So it equals means what? Whatever value of x you take in this interval, you will get sin x equals to this value. When you substitute x equal to 1 here and x equal to 1 here, you will get the same value.
सर हमने रेशियो टेस्ट तो सीक्वेंस पे अप्लाई किया ना, सीरीज पे नहीं किया.
Ratio test is, I think, available for both of these.
यस
But
सर, पर शायद हमने अप्लाई इस पे किया है.
for sequence, if ratio is less than 1, then I think the sequence converges to 0. Some result is like that.
ओके ओके.
So you see that IIT Kanpur notes, in sequences it is mentioned there.